In this problem, we're going to look at a heating curve and we're going to figure out the total energy needed for this entire process. Now, when we look at this, we have to break it down into parts. We got a couple of different things happening here, and we have to look at the energy for each separate process. First, we have ice here at minus 35 going to 0 degrees Celsius. And so we have our ice heating up, so our ice is warming. That's what we're going to call step 1. Then here we're going from ice at 0 degrees Celsius to liquid at 0 degrees Celsius. So we have melting occurring there. We're going to call that step 2. And then we have our liquid water going from 0 degrees Celsius to 65 degrees Celsius. And so then we have again heating our water. And so we're going to call that step 3. Now we could go on up to 100 degrees Celsius, look at another phase change from liquid to gas, and then heating the steam, but we aren't asked to do that in this problem because it's asking us to go from minus 35 to 65 degrees Celsius. Now what we want to do is look at each individual step. And so what we want to say is for step 1, we have our sample. We have 25 grams of water, and we're going to use the formula Q equals mCs delta T. And what this will allow us to do is to figure out the heat required. So we know the mass is 25.00 grams, and the specific heat of ice is 2.09 joules per gram degree Celsius. And our delta T is going to be our final temperature, which will be 0, minus our initial temperature, which is minus 35. Remember, we don't have to worry about converting to Kelvin because we're looking at delta T's. And when we do this calculation, what we find is that we have 25 times 2.09 times 35, and we get 1829 joules. So Q equals 1829 joules, and that is for step 1. Now we can look at step 2, and we can find the energy associated with that step. So step 2, in this case we have to look at the enthalpy of fusion here. We can't talk about Q equals mCs delta T because there is no delta T happening. And so what we want to use then is the energy required to melt that ice, and that energy difference is 6.02 kilojoules per mole. So we have our heat for this step will be equal to N, or the number of moles, times delta H of fusion. But we don't have moles, we have mass, but I can find moles if I know mass, which is 25.0 grams, and use the molar mass of water, 18.01 grams per mole. Now I can use my delta H of fusion, which I can look up and find that it is 6.02 kilojoules per mole. But I see this is in kilojoules. I see my other Q value is in joules, so I'm going to go ahead and convert that because I want everything to be in the same units. So I have 1 kilojoule equals 1,000 joules. And if I look at my units, what I see is that grams cancels with grams, moles cancels with moles, kilojoules cancels with kilojoules, and I'm left with joules. And when I do that calculation, I have 25 divided by 18.01 times 6.02 times 1,000, and I get Q equal to 8356 joules. Okay. So that gives me Q2. Now I'm going to look at the third step, so I'm looking at the third one. Again, I'm looking at a temperature change, not a phase change. So for temperature changes, we use Q equals mCs delta T. Our mass is still 25 grams. Our heat capacity, however, is now different because we're talking about liquid water, and that is 4.18 joules per gram degree Celsius. And we're looking at a temperature change from 0 to 65, so our delta T is equal to 65. And I can solve that 25 times 4.18 times 65, and I end up with Q equal to 6793 joules. So now I have 3 values. I have for step 3 here, step 2, and step 1. And all I need to do now is to add these three values up. And when I do that, I have 1829 plus 8356 plus 6793, and I get 16,978. So the Q total is 16,978. And I can convert that to kilojoules if I want. So this is in joules. And if I want to put it in kilojoules, I simply divide by 1,000. And to convert to correct number of sig figs, I end up with 17, because I need 3 sig figs there, with 17.0 kilojoules. So that's my final answer. It tells me how much energy I need to do this entire process. Note that all my values are positive. This is to be expected when we're heating a sample. It takes energy to heat the sample, it takes energy to melt the sample, and finally it takes energy to heat the sample again. If we were doing the opposite process, where we started at a higher temperature and we're cooling or going in the opposite direction, freezing for example, or condensation, then I would have all my values as negative values, because those are all exothermic processes. So make sure before you add everything up that you have the right signs on everything, and if not, go back and find the loss of a negative sign somewhere along the way. It's frequently in somewhere like this where we invert our final and initial temperatures.